Hi, I'm Shamali Chatterjee, and I will tell you a little bit about what we do in our lab. Our lab is called the Innovatory for Cells and Neural Machines, ICAN. That's the logo for our lab, and we have funding from a number of different agencies, National Institutes of Health, Army Research Lab, Wabash Heartland Innovation Network, which is from the Lilly Endowment. And in the past, we've had funding from National Science Foundation and Northrop Grumman. You can read more about our lab at schatterjee.io. That is my Twitter handle, and our team is at ICAN Students. So I will be telling you a little bit about on-device computation in this short presentation, but we do both design scalable data lakes and we do on-device computation for one of the thrusts of my lab. So the two thrusts in my lab are digital agriculture, or more specifically, Internet of Things for digital agriculture. And the thrust 2 of my lab is mostly to do with computational genomics and genomics data science. The foundations that connect both these thrusts in my lab are applied artificial intelligence, scalable data lakes, and IoT, which stands for Internet of Things, edge cloud computing. These are some of the notable results from our lab. The first one came out of a National Institutes of Health R01 grant that we have ongoing, and we are supporting cyber infrastructure, both database and analytics, for the largest metagenomics portal and data store in the world for analyzing the microbiome, and is called MGRAST. This is a collaboration with Purdue's College of Science and Argonne National Lab. So Purdue's Colleges of Engineering, Agriculture, Science, and Argonne National Lab. The second one, we are developing the only distributed NoSQL database. So NoSQL databases are mostly used and designed for scalability, and these can be configured on the fly based on the kind of workload that is intercepted by the database. And this is also suited for IoT data lakes, where you oftentimes have these fast-changing workloads. And we have published in Middleware 2017 and Usenix ADC, and this is also ongoing work. The third one is to do with genomics data science. So can we think of the genomics language as being the computation of the genome? So can we think of the computation of the genome rather as being a kind of a language of the genome? And can we decode that or decipher that using natural language processing techniques? And using this, we have started doing error correction for both short reads and long reads. And we have seen that the kind of error correction that we do also results in improved assembly. And this has been published in Nature Scientific Reports. The fourth one, like I said, we are very interested in genomics data science, and more specifically, can we translate the genomics data science part into development of precise RNA-based therapeutics and developing them in a cellular context-aware manner. So we have been doing this for the last several years, and we have also won the Best Paper Award in ACM's Top Bioinformatics Conference. And finally, mostly I will talk about this point number 5, where this is ongoing work, and we are developing neural networks, but for resource-constrained IoT and edge platforms. So we have 2 papers and a submission, and we have a couple papers that is in CS Computer Science Archive and on its way to publication as well. So why is machine learning needed in scenarios like this? And when I say scenarios like this, like I said, we have funding from Army Research Laboratory. So where you see agents here, these are intelligent agents, and some of the scenarios here are military scenarios, right? So consider that we want to do local processing or near neighbor processing for efficiency and scalability, and also for low latency, right? So you want low latency, you want high throughput, low latency. Oftentimes, latency is the more important criterion here. Say there is a video event stream and there is a rapid movement in the scene. So can you do quick object detection and then object classification to see what happened at the scene, right? So the agents, or the intelligent agents, need to arrive at a consensus on the knowledge item. from that video event stream. It could also be an audio event stream. And then the agreed upon item, knowledge item, is conveyed to mission control, right? So you basically want to do this processing in an intelligent manner, but you also want to do it with low latency. And oftentimes this will require on-device processing or in-sensor analytics rather than moving on to the edge or cloud for low latency. So an example where you might want to do this low latency analytics might involve these deep learning algorithms, right? So deep learning is ubiquitous these days, and two of the reasons why deep learning is ubiquitous is because there is a lot of data and there is a lot of compute to throw at this data, right? So oftentimes you need a lot of computation, and this computation is done using a GPU backend rather than a CPU backend, right? But what happens is, as a result, you might also need a lot of energy. So oftentimes these days, you basically want to do the computation using neural networks, but using an energy-aware neural network where you decrease the energy consumption of the neural network. And we will talk about that a little more in the next few slides. But let's talk a little bit about object classification, right? So you can read more about object classification. This is to whet your appetite a little bit. So what you see in this image is you see a girl riding a bicycle, and you don't see the girl with a beer bottle in her hand, but I guess the algorithm is smarter than you think, and it gives a beer bottle a score of 0.342. But we see that the algorithm is doing pretty well in that it's giving the bicycle a score of 0.890 and the girl a score of 0.731. So these are the different image categories, and these are the predicted labels. And you might have heard of the popularly used data set called the Net Dataset. Just to tell you a little bit about it, it has 14 million images, and these 14 million images have been hand annotated into 1,000 different classes, right? So each of the images you tell us what the class of the image is, and this has been hand annotated, right? These days you have more ubiquitous data sets. When I say ubiquitous, I mean they have a lot more categories or a lot more classes of images, which might also include more esoteric classes, right? But the ImageNet dataset is a widely popular dataset, and I give you an example of what an object classification algorithm might be doing, right? So you will have these different object categories, and you will have the corresponding predicted labels next to the image categories. So this is essentially what object classification is. Now, once you have classified the object, say there are multiple objects, right? So you might also want to localize the object. So localization of objects is done using something called bounding boxes. So you see a red bounding box. In fact, you see two red bounding boxes. You see a blue bounding box, and you see a green bounding box. So for example, the blue bounding box is the bounding box for a dog, the green bounding box is the bounding box for a duck, and the red bounding boxes are bounding boxes for cats, right? So it is correctly using the red ones for cats, the blue one for the dog, and the green one for the duck, right? Now, one thing to remember is for any kind of a machine learning task, you want to see what was the performance of the model, right? So being able to detect or being able to quantify the performance of the model is very important for any machine learning task. Likewise, in this task, where you have object localization and detection, these are the popularly used metrics in computer vision to be able to see how well the model is performing, right? So in this case, you see you have IOU, which is the intersection of union, and this is based on knowing the ground truth, right? So if you know the ground truth, and if the IOU is greater than a certain threshold, this can be a user-defined threshold, then the object is considered to be detected. And what IOU is intersection of union. So it's the area of overlap that you see in the numerator divided by the area of union. So this is one of the popularly used metrics specific to computer vision, and the others are ubiquitous in machine learning, precision and recall. So for each object class, you calculate the recall, which is true positive divided by the number of ground truths, which is true positive plus false negative. So in the numerator, you have true positive plus false negative, which is the number of ground truths. And in the numerator, you have the true positive. That is the recall, whereas the precision is the true positive divided by the number of predictions, which is TP divided by TP plus FN. So these are the ones that are used in all of machine learning. But intersection of union is something that is used in computer vision to measure the quality of the algorithm. Now, one of the things that resulted in the success of deep learning, right? So I'm sure those of you who are listening to me might be familiar with deep neural networks. So deep neural networks, they are not shallow neural networks. And typically what happens in a deep neural network is you have multiple hidden layers, right? So you have an input layer and you have an output layer, right? So input layer where you have the inputs coming in, and the output layer typically where you have a soft max classifier and you'll get the final classifications. So in between, you have a number of hidden layers. And depending on how deep the neural network is, you might have multiple hidden layers. And typically for a deep neural network, you would at least have 2 hidden layers, maybe to qualify as a deep neural network, as opposed to a shallow network. So in the past, you had multi-layer perceptrons, where you just basically have an input layer, you have a hidden layer, and you have an output layer. But what happens in a deep neural network is you have multiple layers, and these multiple layers give the input features a lot of non-linearity. So you have the first layer of non-linearity, and then it is compounded by additional layers of non-linearity. And finally, you might have a soft max classifier that results in the final classification. And this classification, like I showed you, could be one of 1,000 different classes, as in the ImageNet dataset, right? So the ImageNet dataset, you have labeled images. And then, so a lot of data, a lot of labeled data, that is important, right? So you have a label for, so if there is a cat, that would have the corresponding label that this is a cat. So that's what we mean by labeled images. And then you have complex models. So a lot of the times in computer vision, you have these models that have multiple parameters. For example, VGG has as many as 138 million parameters, and it trains on 4 GPUs for 2 to 3 weeks. So I wrote these down because these are, pretty intriguing numbers, that a VGG, which is considered state of the art in some way, it has 138 million parameters, and it trains on 4 GPUs for 2 to 3 weeks, right? So you wouldn't call that very efficient. Just another trivia, it uses something called Gabor filters, Gabor. Whereas Inception is a more computationally efficient model, and it uses 25 million parameters. So just some trivia again, VGG uses 138 million parameters, whereas Inception uses 25 million parameters. So what is VGG and what is Inception, right? So these are convolutional neural networks, also called ConvNets or CNNs. And convolutional neural networks, they are the specific kinds of deep neural networks that are used when there are images, lots of objects, right? So when you have images or objects, then the kind of neural network architecture that you use are ConvNets or CNNs. That stands for convolutional neural networks, right? So you can read about them ubiquitous in different places in the web, or you can take a course in Coursera. But essentially what these are really good at is these are really good at being able to detect objects or classify images, etc. One important thing that we saw is these are really complex, so they may not necessarily be computationally efficient. I gave you these numbers to remember as trivia: 138 million parameters in VGG, whereas Inception took into consideration computational efficiency and has a lower number of parameters, 25 million parameters. And it has these things called inception blocks. And one of the ways in which it is computationally efficient is by using batch normalization. In fact, there are 3 things, and you can read about them a little more. Batch normalization, image distortions, and RMS prop. So these are 3 of the characteristics of the inception ConvNet that makes it computationally efficient, that it uses a lower number of parameters and also has pretty good performance, right? So a little bit more trivia is LeNet was started in 1998 it was a 7-layer convolutional neural network, right? So I told you the number of hidden layers in between the input layer and the output layer is what defines the depth of the neural network. In this case, whenever you're doing something to do with images, it's a convolutional neural network. And Linnet was started in 1998. It was a 7-layer convolutional neural network. Whereas AlexNet, what happened is it started using a lot more parameters. AlexNet specifically has 60 million parameters. It trains on 2 GPUs for 6 days, right? So one of the differences, if you think about it, is AlexNet. It has 60 million parameters. VGG has 138 million parameters. You also see this VGG here. VGG16 is a specific VGG model, which is possibly a 16-layer VGG, right? And then we have Inception, which has 25 million parameters. And what Inception did is it brought into context computational efficiency, that you may not always want more compute and more complex models, but you might also want to think of computational efficiency if you want these models to translate to real-world applications, right? So on the left, what we have essentially is these 3 factors that resulted in the success of ravishing success of deep neural networks: more data, complex models, and then more compute, right? So you have these GPUs that you can throw at these complex models to be able to run these models faster. But even with GPUs, for example, I told you VGG trains on 4 GPUs for 2 to 3 weeks. Right? Whereas in the past, AlexNet, which was in 2012, it trained on 2 GPUs for 6 days. So obviously, as you have more number of parameters, it is also taking longer to run. And one of the things that happens along with that, along with the increased runtime, is it takes a lot more energy. Right. So now on the right is some of the stuff that is motivating work in our lab, is that you don't always have more data. In some domains, you may not have more data. For example, if you consider in the digital ag domain, if you consider LiDAR data is extremely difficult and expensive to annotate. So oftentimes you don't have labeled data sets. And in fact, labeled data sets, there are companies that are out there just to be able to create more labeled data sets because of the paucity of labeled data sets in some domains, right? The other thing is you don't always want very complex models, and sometimes you might want to run these models on resource-constrained devices, right? So for example, you might want to run these models on Tegra TX2 boards, or you might want to run these models on Raspberry Pis that don't even have a GPU. Right? So some of the times, the original factors that resulted in the success of deep neural networks may not be there at our disposal. And what do you do then, right? What kinds of considerations do you have to take in order to design deep neural networks that can run without having tons of labeled data sets, without necessarily using very complex models or very powerful GPU backends? So I told you in the past, computational power plus lots of data resulted in complex DNNs. But DNNs in industry, slowly what happened is they tried to get into this area of computationally efficient DNNs. In Google Brain, in NVIDIA's network, Baidu Brain, Livermore Brain, can we do more with less, right? Some of the things that you use is parallel structural optimization. You can go look that up. But essentially what we're doing is we are trying to decrease the number of parameters that are needed to run the model. And this is something that is happening now, that people are taking into consideration the number of parameters and essentially the runtime and the energy requirement for these models. So object classification and detection on the edge. So instead of doing all of that on the cloud, can you do some of that on the edge? And when I say edge, these are resource-constrained devices, or you might also want to do some of this computation on the sensor itself. So on-device computation or computation on the edge, as opposed to computation in the cloud, where you have a lot of resources, computational resources at our disposal. So this is an example of IoT applications. You see a 3-tier platform for IoT applications. So on the left, you have data being generated from these different IoT applications that rule and reign our worlds today, AR, VR devices, security or monitoring devices, these Nest thermostats, smart appliances, etc. And then you might have to run a lot of this on the edge, right? So these are examples of where you have low-end GPUs or server CPUs or low-power CPUs that have to do this kind of computation rather than offloading the computation on the cloud, where we have essentially computationally infinite resources, so no real constraints on the resources. So you see high bandwidth services on the left generate high bandwidth data. This data could be, like I showed you early on, it could be a video stream or it could be an audio stream. And then you could also have low bandwidth data. So what we've done in some of our experiments is we've basically played around with high bandwidth services and low bandwidth services. So low bandwidth services are actually important. You have lots of data coming from these different environmental sensors. For example, as a part of the WIN project, the Wabash Heartland Innovation Network project, there are various kinds of sensors that are being deployed in farms and buildings, right? So if you think of farms, you have moisture sensors, you have nitrate sensors, you have humidity, temperature sensors. And what we need to do is we might want to aggregate and process a lot of that in the gateway devices rather than taking all of that to the cloud, right? So that would result in lower latency. It would also result in higher efficiency of a lot of this computation. So what are the challenges of running on the edge, right? So we want to run analytics on live streams. So taking the example from before, you have video from the ground of civilian or military space that is being explored, right? But we want to run them on resource-constrained mobile and embedded devices, or we want to run them on edge computing platforms as opposed to the cloud, right? So why do we want to do this? One, bandwidth to the cloud is expensive. We may be in a network-starved region, which may be common in military warfare scenarios or even in digital agriculture, where you have these farms that may not be that may be network starved rather. And then the centralized solution cannot scale up, right? So that's how you might want to do some of this computation on these resource constrained devices. Now, most video analytics queries involve performing inference over CNN. So we talked about CNNs, right? Convolutional neural network architectures that are mostly used for video analytics. So when you think of computer vision, you think of ConvNets or convolutional neural networks. And these are too slow on edge devices to keep up with the video stream rate, which is typically 30 FPS. FPS stands for frames per second, or they are too memory heavy, right? So memory heavy is 4 to 8 GB per model, right? So these models, when I say model, these are the machine learning or the analytics models. And mostly, if you're considering video analytics, these would be neural network models, right? So they are too slow on edge devices, right, to keep up with the live video stream rate. And the stream rate is measured in frames per second or FPS, and a reasonable frames per second or a stream rate is 30 FPS. And sometimes they have too memory heavy, right, 4 to 8 GB per model. So these are just to give you some of the challenges of running these models on the edge. So what is the solution, right? So we have come up with some solutions. For example, we can approximate an embedded GPU. So we speed up the object classification or the object detection by running on an embedded GPU, the accelerator of choice, right? So these embedded GPUs are now all over the place. And an example of the ones that we are playing with are NVIDIA Tegra TX2. So we are using these NVIDIA Tegra TX2 boards, for example, to speed up object classification and detection. So even though it's an embedded device, it has a GPU backend as opposed to a CPU backend, right? As opposed to only a CPU backend, I should say. But just this does not solve the problem, right? Why does it not solve the problem? Because inference of one image on ResNet-34, ResNet-34 is an architecture, a specific architecture, and it's one of the most popular DNNs for object classification. And inference of just one image takes 64.4 milliseconds. right? Object detection for one image on faster RCNN with ResNet 50 as feature extractor takes 723 milliseconds. Now, faster RCNN, the reason I mentioned that here is faster RCNN is used for computer vision, and it is also used to run some of these vision algorithms on these embedded devices where you don't have as much compute. So it is computationally resource constrained. Now, what our goal is to have an inference time of 33 milliseconds per frame for a video. Whereas we see in this case, in the first example that I gave you for ResNet 34, object classification takes 64.4 milliseconds just for one image, whereas object detection for one image on faster RCNN takes 723 milliseconds. And our goal is to have an inference time of 33 milliseconds per frame. This is just so that you don't have very grainy videos, right? So this is what has been found to be optimal. Now, because it does not solve the problem, just having this GPU board does not solve the problem. So what do we do, right? So there are different ways in which we can approximate the processing or approximate the analytics. One way would be to downsample the image size, right? So downsampling. Another way would be to do an early exit from the CNN. So think of this, if you have, so we talk to the architecture from left to right. Now let's turn it over 90 degrees and think of the architecture from top to bottom, right? So you have the inputs coming in, you have the input layer, and then you have multiple hidden layers, and then you have the output layer, right? So instead of outputting, say, from the nth layer, you output from the n minus x layers, right? So that you have an early exit from the CNN instead of doing the processing all the way to the end, right? So how do you do this early exit, right? There are ways of doing that. And the other thing is you change the number of proposals that faster RCNN makes. So region proposals is something that this faster RCNN model uses. So you change the number of proposals in order to approximate the analytics for object detection, object localization, etc. Right? So these are some of the ways in which you can approximate the analytics. Because we realize that only by using an embedded GPU, you cannot solve the problem of being able to run these bulky models on these resource-constrained devices. So here is some related work that you can see. We have ResNet, MobileNets, and faster RCNN. SSD is a different kind of architecture, and it's a popular object classification detection model on images, but these may not be suitable for streaming videos. MCDNN, what it does, it's an ensemble method where you have a large number of models, and by using the right model, you come up with the approximation. But one of the things that happens is if you have an ensemble of model, there is a certain latency to switch from one model to the other. So we basically want to decrease the latency of this switch, right? So if you have a larger, a bulkier model, and you have a smaller, a less bulky model, switching from a bulkier model to a less bulky model based on what the context is takes some time. So we want to reduce that latency of the switch, right? And MCDNN basically does not help with that because it's an ensemble method where you have multiple models to choose from, and there is a huge transition overhead. So the shortcomings of the current solutions, we saw model compression, a specific model design for mobile embedded are successful in statically trading off between accuracy and latency, right? So if you have, if you want high accuracy, you want a less compressed model. You might want the full-blown model, right? But then if you basically want to decrease the accuracy because you care more about the latency, that is, you want the analytics to happen fast, you might want to compress the model, right? But being able to do that on the fly is hard to do using current solutions. The second thing is mobile or embedded devices, the runtime available resources can fluctuate due to co-locating with other background applications. So typically in a real usage scenario, you basically have multiple co-located applications running on that, say, Tegra TX2 board. Or if you're if you don't have Tegra TX2 boards, that can be hundreds of dollars, about $500 a piece. Raspberry Pis are 50, and you basically, and there is, it doesn't even have a GPU, but being able to co-locate different background applications becomes trickier and trickier as you have more inexpensive devices. Now, models such as MCDNN, which is a Mobisys 2016 paper, it has a huge latency spike because you essentially have to move from one model to another. So these are some of the shortcomings of the current solutions to be able to run these bulky models on resource-constrained devices. So we have approximated versions of these computer vision algorithms, and what we have seen is, as a result of our approximation techniques, we can reduce the latency spikes. So what you see here is, in blue you have our solution, and in red you have MCDNN, which I said is an ensemble of models. It's a Mobisys paper, so you can go look that up. On the right axis, on the vertical axis, you have the latency in milliseconds. On the horizontal axis, you have the frames. Right? And then what you have here is HHMMLL. So HH stands for high accuracy, high latency. MM is medium accuracy, medium latency. And LL is low accuracy, low latency. And HH offload is the accuracy required by the client is so high that you would have to offload. When I say offload, it means offloading from the edge or from the device to the cloud, because you need more compute to be able to get the kind of accuracy requirements that the client is asking for, right? So what you notice here is an MCDNN, which is in red. You have these large spikes, right? So these vertical spikes in the MCDNN, when you have these switches being made, you have these spikes. Whereas in our solution, you don't see these spikes, and the latency overall is also much lower. The second thing is what I said is you have lots of normal background processes, right? So for example, think of the graduate student checking email while this is running, right? That is not a very high bandwidth background process, but they can be higher bandwidth background processes that are co-located while the actual application is running, right? And if you have these background processes, that results in GPU contention, right? So Tegra TX2, like I said, has a backend GPU. So here what you see is, if you see that 5-pinned bubble of 10 KB and then 5-pinned bubble of 300 MB. So you have a co-located application, 10 KB versus 300 MB, and then 5-pinned versus 5 unpinned bubbles. So when you have an unpinned bubble, it results in higher contention. So what we do is we try to play with the level of contention, both pinned and unpinned, and also the memory, right? So 10 KB versus 300 MB. And what we see is our solution is able to handle this better, whereas an MCDNN, the latency significantly increases as a result of this increasing contention, which is increasingly violating the video latency requirement that we talked about. So novelty of our proposed technique, we see that we actually have one model to trade off accuracy and latency. So we use different kinds of approximation knobs within one architecture, rather than having to switch between different architectures or switch among different architectures, such as in the MCDNN scenario. We also have a contention-aware adaptation. So we have used a synthetic contention generator to represent workload contention in different dimensions, 3D dimensions of CPU, RAM, and GPU. And then we also have a lower switching cost and higher performance as a result of this contention-aware adaptation. The final thing is the adaptation is also content aware. So if you have a video that is really complex, you would have to need to come up with lower approximation in order to keep the content more palatable. Whereas if you have less sophisticated video, say someone is sitting and watching, versus a soccer game going on. A soccer game going on, you would need less approximation, whereas if there is a very static video, you could do with more approximation. So that is the content-aware part of the solution. And finally, here what we show is adapting to changes in requirements, right? So we talked about this a little bit, where you have high accuracy, high latency, HH, medium accuracy, medium latency, and then low accuracy, low latency, and finally you have HH offload. So what we see here is, as a result of increasing GPU contention level, I told you that you would have background processes occurring, and we have come up with a way to increase the contention. So we see that as a result of increasing the contention, our solution maintains lower latency of about 33 seconds or milliseconds or under, whereas in the case of MCDNN, there are latency spikes as a result of changing contention, GPU contention in this case, because mostly if you have neural networks running, you would have GPU at the back end. The other thing we talked about is changes in image, so content-aware approximation. Finally, this is to give you an example of the different kinds of embedded devices that are being used for distributed ML at the edge. Of course, the price points are different as well. You have a $50 Raspberry Pi, roughly, versus a $500 NVIDIA Jetson TX2 board. So this would be an example of a low bandwidth operation, right? Anomaly detection that could be running in the background. And if you basically wanted, we could have like something like an RNN, recurrent neural network, doing very precise anomaly detection if you have lots of data sets and lots of different kinds of sensors. So this could be another kind of operation in addition to the computer vision application, right? So we are also doing approximation and on-device computation for anomaly detection, because that is very relevant to some of the sensors that have been deployed as a result of the WABA Shortland Innovation Network project. Different kinds of sensors that are measuring parameters, environmental parameters such as temperature, humidity, soil nutrient quantity, soil nutrient quality, which is quantity of nitrate, phosphate, etc. So this is just an example to show the different kinds of data sets that are being generated by these devices that are being deployed in different parts of campus and different forums. And with that, I'm going to end. This is our lab. A portion of my lab, about 50-50, does genomics data science, whereas the other 50% of my lab is involved in these kinds of IoT-related digital agriculture solutions. Like I said, in the digital agriculture space, we're working on both engineering and architecting scalable database pipelines, and also coming up with on-device computation. So how do you onload the computation on the device or on the edge device rather than always offloading to the cloud for scalability reasons, for latency reasons, and for energy-aware computation? Thank you.